Hey guys, I'm going to go ahead and get started. Mike's not here with me today. You might see I'm logged on as Mike. That's really just so I can start recording these things as we do them. Because one of the things we want to start doing, we want to have this as a resource to pass to new people that we hire along the way, as well as, training right now. So we might be like creating a small YouTube page or something where we just put our, these recordings here, we'll just upload them onto there. So if you ever need to go back and revisit something, maybe you've forgotten something, um, we'll try to make it readily available. And we're thinking YouTube's probably the easiest place to do that. Whenever that happens, I'll send out an email or something, let everyone know. Um, Also, one other thing that we're going to have going on is I'm going to send out some emails that will actually include some other YouTube videos that get a little more technical, a little more in depth into how this electricity stuff works. Um, you've probably noticed we've been really skimming the surface on a lot of this, and we're kind of explaining basic concepts, but we're not getting into the math or the engineering. And that's because the purpose of these videos, the purpose of our training sessions, is to focus on installing fire alarm systems, maintaining, servicing fire alarm systems, and then testing them. So we're not really worried about making a whole bunch of junior electrical engineers or anything. So we're kind of skipping the whole engineering side, and we're going for more of a practical knowledge that's more helpful in the field. So just know, be looking out for those things in your email. If we're not like requiring that you go and watch those YouTube videos I send out, but if you're interested, if you want to know more, that they'll be a really good resource for you to kind of put some effort into on your own time to, just pursue more information. Hold on, I didn't skip. So first up, I want to start by reviewing a little bit of what we talked about last week. We talked about the basics of electricity and then how to measure those things on a meter. And so I wanted to revisit this picture here where you have your voltage. I want to remind you is like the pressure. We talked about if you have a water hose, the volts are the water pressure pushing the water through the water hose, where the amperage would be how much water is getting pushed through that hose. And a little bit later, I'm going to talk more about voltage drops and give you kind of an idea of what those are. We're not going to go real detailed into those either, but just to give you an idea of how they work, I'm going to continue on that water hose metaphor. And then we talked about ohms being the resistance. It's things that slow down or limit the amount of water that goes through that hose. And today, when we're talking about Class B circuits, that relationship between the amps and the ohms is going to play a big part in how Class B supervision works. So I want to take just a second to explain that. So when our ohms get higher, meaning we have more resistance on the circuit, we're going to have less amps that can flow through our circuit. There's going to be higher resistance means lower current. So if you look at this picture, you can see the red guy, he's pulling on a rope, tightening up that wire around the little green guy. And that's kind of what it is. The harder the resistance pulls on it, the more resistance there is, the harder it's going to be for the amps to get through. So you're going to have more resistance means less current. And then, of course, the opposite is true as well. The less resistance you have, which would mean that red guy is loosening up on that rope, the easier it is for that green guy to get through. The more current will get through with less resistance. So just we'll revisit that that explanation here in a minute whenever we get into Class B supervision and the current flow and that kind of thing. Also, I want to apologize. Right when I was setting all this stuff up, my camera took a dump on me and it started flickering, making it look like it was some kind of rave or something. I even got calling on a separate little video call to see if it was maybe working on y'all's side and just not on my side. But the camera went out, so I'm not going to be able to do a hands-on meter part today just because that camera just fell apart on me here in the last like half hour. But we're going to get another camera, and I'll have to make it up in the next video or something. So this slide here, this is just a copy paste of the definition of a Class B circuit found in NFPA 72. NFPA 72 is the fire alarm, fire code book. Currently, Texas is under the 2013 edition. Every 3 years, they come out with a new NFPA 72, but just because they come out with a new one doesn't mean that we've actually adopted it. But Texas is under the 2013, so they have a 2016 and a 2019 that's come out, but the changes in those don't affect us yet, and they won't until we adopt either one of those code years or a code year that comes after that, because then all the preceding things will kind of spill into that. So in NFPA 72 chapter 12, it's a very, very short chapter, and it's one of the worst and most horrible chapters to read, even though it's only like a page and a half long. It just defines the different classifications of circuits. And in the 2013 edition, there's only 6 classifications of circuits. In the newer ones, they added a 7th classification, which honestly is a completely pointless one. It's a class N, and it's just Ethernet. Like, it's something that's already been being put in buildings, but NFPA 72 has some official somewhere that needed to write down a definition for it and call it his job. So reading through these real quick, these definitions define what a Class B circuit is. These are the most common circuits that you'll ever see in a fire alarm system. So the first point is it does not include a redundant path. That's what really separates it from a Class A circuit. And at the end of this, I have a quick picture I'll show you of what a Class A circuit looks like. We do very, very few of them. We don't like doing Class A circuits because they're just more work and there's not a lot of benefit from them. The second point is one that we get most of our problems from, and that's operation capability stops at a single open. So that's anywhere in the circuit. If one of your wires comes disconnected, every device after that wire is going to stop working. That's what that means. And then you see conditions that affect the intended operation are enunciated as a trouble. That just means that if that circuit opens, the panel is going to give us a trouble about it. And then you have a couple points about ground faults. One is that if you get a single ground fault on the system, the circuit will continue to work, but then it'll also tell us that there's a ground fault. If you get multiple ground faults, it's able to take the circuit down. One of the trainings I want to do in the near future is one that is specific to ground faults, how to chase them, how to get rid of them. Ground faults are one of the worst parts of a fire alarm system. We all hate them. There's not a single person on the planet that just says, oh, goody, I get to chase a ground fault today. They're awful, elusive jerks. And so we'll do a training on some of the best ways to most effectively attack them. And even with the best ways, they still suck. But knowing what you're doing when you're chasing them helps them suck a little bit less. So some common examples of Class B circuits. I have a few pictures up there. The top right picture is a smoke detector that is actually a conventional smoke detector. Those are hooked up on what are called IDC circuits. They're initiating device circuits. That's how fire alarms used to work before technology started advancing and we started having digital communications. They work very, very similarly to how our mini modules, our monitor modules work now. And so what'll happen, that'll actually be powered by a 2 or a 4-wire circuit. If it's a 4-wire, just 2 of those are just aux power to bring power to the device, and the other 2 would then be like a monitor module. And if that device gets smoke in it, it just flips a set of contacts that shorts it out and closes it. And the panel would then see that short and trigger an alarm. I'll get more into shorting and closing and relays. That's another one that I want to do, is we want to talk about relay logic and wiring different relays together to do different functions. And so we'll probably I'll bring IDC back up a little bit in that one. Conventional stuff's not something we deal with a whole lot. Sometimes we might see it in like a small apartment complex where we're doing sprinkler monitoring. Other than that, we kind of try to avoid it. It's a very cheap system to put in, but it doesn't work nearly as well as the addressable. And that's what this other smoke detector is. You see, it's kind of the one in the center, more or less. These are the new addressable smoke detectors. And those work on our signaling line circuit, which we call short SLC. So that's another type of Class B circuit. And then in the bottom right, I've got a picture of a strobe there. That's a notification appliance. So the circuit that powers it's a notification appliance circuit or a NAC circuit. So we have our horns and strobes that are NACs, and then also speakers. Our speaker circuits technically count as NAC circuits in all ways that the code defines it, in all ways that everything defines it. But in specs and a lot of times from manufacturers, they'll actually refer to speaker circuits separately from NAC circuits, even though they're the same thing. So I put that little asterisk by it just because. And then down at the bottom, I put RS-485 and S-Bus. Those are other types of Class B supervised circuits. RS-485 is like the annunciator circuit we would use on Gamewell stuff. Also Firelight and Notifier and all that, they call it RS-485. Silent Night renamed it S-Bus. It basically works the same way. So I've stuck those together. So in this next one here, first I want to talk about my pictures I got down here at the bottom, I guess, before I get into everything else. So on the bottom left, you see we've got a fire alarm control panel. And then I've got all those circles represent a device. And this could represent either a NAC circuit or it could represent an IDC circuit, where you see how it daisy chains from one device to the next with both a red conductor and a black conductor, going all the way to the end where there's an end-of-line resistor. And so this is, if your Class B circuit, everything in it works just fine. This is what it's kind of looks like drawn out like this. The picture on the right-hand side, you can see I put an arrow drawing to where there's a broken wire. This would be an example of an open circuit. There is now a part of the circuit that is no longer connected. So the connection is open. And you see the arrow pointing at all the devices after that. Those devices no longer work. That was one of those defining characteristics that separates a Class B circuit from a Class A circuit. Whenever you get that single open condition, everything after it will no longer work. So to talk about using our meter, when we use our meter, we're going to look at, well, we'll look at 4 different things, but today we're going to talk about 3 of those 4. The 4th one is ground faults. I'll save talking about that for when we do an actual ground fault lesson. We're going to look for open circuits, we're going to look for short circuits, and we're going to look for devices that might have reverse polarity. And so we'll talk some about how to see that with a meter too. So the first bullet point I put down, I put, before you land any wires to the panel, we want to check them with our meter. We want to do that for a couple of reasons. One is it's going to help save our panels. You know, if we've got a short circuit on a panel, we don't want to be hooking it up to the panel, powering up the panel, putting the panel in alarm, and then the panel cooks itself because it's got too much current flowing through. And when you get too much current flowing through a circuit, it creates more heat than whenever you have the right amount. And that heat is what actually cooks the panel, because there's so much current going through that the panel actually overworks itself and breaks itself. So kind of going on that, if you look at our good example of a Class B circuit where you have that end-of-line resistor there, that's going to limit the amount of current that goes through the circuit, because what's going to happen is your supervision voltage is going to go down your circuit, it's going to hit your end-of-line resistor, and that's a specified size resistor. That's why it matters from which panel to which panel it goes on. And that's another email I'll send out. I actually put together a table of which type of panels need what type of resistor. So I'll try to send that out to y'all, because I feel like that can be a helpful resource as well. But since it's a specific size resistor, it's going to slow that current down a specific amount, and only that specific amount of current is going to be what makes it back to the fire panel. And your fire panel is looking to make sure it has the right amount of current flowing through the circuit. So if it was a water hose, it would be an exact amount of water flowing through the hose. And if it has too much water, then it's going to call it a short circuit. And if it has too little, then it's going to call it an open. Except instead of water, it's electricity. Don't put water in your fire alarm panel. So to look for that specifically, I'm sorry, I'm getting ahead of myself. So we want to check all of these circuits to make sure we have the right amount of resistance on the circuit before we hook it to the panel so we don't get too much current flowing through it. So that's one reason we want to check it with our meter before we ever land it to the panel. The other reason, even though it's an extra step, it'll actually save you time in the long run to do it this way. If you don't check these things and you hook it up at the last minute and you're crossing your fingers and you're hoping, you're saying no ground faults, no shorts, come on, let's, you're really hoping for it the day that it's time to turn on the panel, then you're kind of waiting till the last minute, and any trouble you get is going to start delaying your job and start slowing you down. We've all experienced this on whether it's been your job or you're having to go help someone else's job. And it's always one of the worst parts of the job, because you have all the other contractors who are on you saying, come on, we need to see lights and strobes. Come on, we need to get our final done. Come on, the customer wants to move in. And we're like, but we got to get this working. Hold on, back off, give us time. Well, by checking it with our meter, we're not waiting for any of the other contractors like the electricians to get our panel put up, or we're not waiting on our programmers to get there to know if your stuff works or not. You're able to check it well ahead of time. So if you worked hard that day and you put in a whole bunch of NAC circuits and you got all your circuits trimmed out, take a few minutes at the end of the day, instead of saying, okay, it's 3:30, now I'm going to start packing my stuff up and put it in the truck. Say, okay, now it's 3:15. Let me go grab my meter and I'm going to go check the circuits we trimmed out today. And then if you have any problems, you're familiar with where the problems are already. You're not going to have to spend time trying to figure out where in the building that problem is, because you just finished working on it. So you're going to know a little better where it is. And that's going to help isolate that down. And doing that every day as you trim devices out, just taking that few minutes at the end of the day to check your circuits, when it does come time that you've finally gotten power from the electricians and you've finally gotten the programmer out there to put it up, you're not crossing your fingers and hoping. You're ready to land those circuits because you've already checked them with your meter and you put it on there, and you're a step ahead of the game, and you know that when it turns on, that circuit's going to be good. There's no hope, it. So those are the couple reasons we want to check them with our meter. One, it protects the panel, and two, it helps you get a step ahead of the game. So in order to check these circuits, it's going to be real similar to what we talked about last week. We're going to set our meters to that O-meter setting that has that Greek omega symbol. And you're going to connect your red leads to your red conductor of your wire and your black lead to your black conductor of your wire. And you're going to see one of three things when you do this. You're either going to see an open circuit, which is a higher, or a value that is higher than your end-of-line resistor. So even if it's not OL on your meter, if it says, you've got 50 K ohms instead of 4.7 K ohms, your panel's still going to read that as an open circuit. So you're going to have to go through and diagnose, okay, why is my circuit open? The other thing you could see is a short circuit. This is any value smaller than your resistor. So say you've got that 4.7 K ohm resistor, but you're seeing, 50 ohms or 100 ohms. That's a pretty hard short, and you're going to have to find that before you hook it up to your panel. And then the last thing you could find, this is a closed circuit. Closed circuits are what we want on, especially NAC circuits. Closed circuits are where you see your end-of-line resistor. It's not too high, it's not too low. You see what you want to see. That's a closed circuit. Everything's able to make the loop it's supposed to make. Now we're going to talk about troubleshooting. So say you didn't see what you wanted to see with your meter. One of the easiest strategies to do to try to find where this is, say you've got it narrowed down to which circuit it is, which area of the building it's in, and this will work no matter how many devices are on your circuit. So if you've got a really large speaker circuit that goes a long distance, or if you've got a NAC circuit that only has a handful of devices on it or anything in between, this method will work. And this method is really what we can base all the other troubleshooting methods that we talk about later on. They can kind of start with this, and we'll adapt this principle to each different thing. And that would be, first, if you're standing at your home run, and we'll say that you see an open circuit, kind of like this picture off to the side here. First step I would say to do, I mean, if you want to, you can just first go make sure your end-of-line resistor is actually installed. Sometimes that's a really easy fix. So if you want to go to your last device first, make sure the resistor is there. If the resistor is there, then come back to the center of the circuit. Now, if you've got an even number, it doesn't matter which of the two in the middle that you get, or if you've got an odd number and you go to the exact middle. The idea that we're going for here is we're going to isolate entire sections of the circuit. And so from that center, you can put your meter facing towards your end of line. And if you don't know which side your end of line is, it might be helpful to keep some extra resistors with you. I recommend finding some that are just a different value than whatever your end of line is. 4.7K is really, really common. So in my bag, I have a handful of 33K resistors, just because that's not a very common resistor, but I picked some up for free one time. And so I'll actually wire up those on the home run side of it, so that whenever I go to a device, and that device has two sets of wires in it, and I know one set's going to go back to my panel and one set's going to go to my end of line, I can put my meter on each one, and depending on what value I see, I'll know, okay, I see 4.7K here in the center, so I know from the middle of the circuit to the end of line, it's good because I see what I should see. I see that closed circuit that has the resistor at the end. But then I turn and I check the other set of wires, and I don't see that 33K ohm resistor that I wired back at my home run, then I know my problem's in my first half of my circuit. So right there with that first step, I've already eliminated half of the circuit. I know I don't have to check any of those devices. All those devices are making a closed circuit. So then what I do is I'll go ahead and connect that device back up so I don't have to come back to it and work twice. And I'll take that first half of the circuit and I'll divide it in half again. And I'll just repeat the same step. I'll check both sets of wires, looking for my 33K ohm resistor and for my 4.7K ohm resistor. And depending on which one I see or don't see, that tells me which direction to continue chasing my trouble. And by doing it this way, I'm continuing to eliminate chunks of the circuit at a time instead of just going device by device. And so if you're working on a really, really big speaker circuit, this eliminates, possibly 20 or 30 devices at a time sometimes. So it's a very time-effective method for chasing it down. If you're troubleshooting a circuit that already exists, maybe it's already hooked up to the panel, but you're on a service call and now you're getting an open circuit on it and you don't have an extra resistor with you, you can also leave that home run landed on the panel. And when you go to each device and you take it down, first put your meter on your direct current voltage setting and check both sets of wire. One of the sets of wire, you should see your supervision voltage, and that'll tell you that's the side that goes back to your panel. And if you don't see it on either, then you know, okay, it's somewhere between the panel and this device that my problem is. But go ahead and flip it over to the ohmmeter setting anyways to check for resistance and make sure you can see your end of line, because you might have more than one trouble on your circuit. And if that's the case, just pick up, just go and whichever one you think is going to be easier to find, just look for one trouble at a time. Don't try to chase multiple troubles at once. You'll end up just making yourself go round and round in circles. Another shortcut that works well on construction sites but does not work in occupied buildings, when you do have an open circuit, so this will only work with an open circuit, it won't work with a short circuit, you can power that circuit up even if you don't have power to your panel, but you got a couple of batteries. You can power it up off the batteries and you can see where the circuit stops working. If you're able to do this, this is a faster way to find an open circuit. Don't do this with a short circuit, because it could actually, depending on how hard the short is, it could even make the batteries blow up in your face, and we really don't want that. But when you do that, you can go to the last device that was working and you can check and make sure that all your wires are connected there. Make sure you can see your end-of-line resistor. If you don't see your end-of-line resistor, again, just double check all your wires, put that device back together, go to the very next device, and from there you should be able to see your end-of-line resistor. And if you do, and you turn back the other way, but you still don't see power, that means that it's actually the wire between those two devices that's your problem. However, if you've got power coming in on the one side and you see the resistor on the other, then that means you've got a connection problem at your device. So you need to make sure all your connections are done correctly. And again, this method of dividing the circuit in half and jumping around, this is going to be something we come back to no matter what type of circuit we're working on trying to diagnose it. It's just a very fast, very effective method. So, you know, if you need to write that down or remember that, practice that, whatever it is that you're going to do to put that into your memory. And as we talk about looking for something more difficult like a ground fault, we'll just take this concept and we'll apply it to looking for the ground fault instead of looking for an open or shorted circuit. And if you're looking for a shorted circuit, obviously you can't power it up. Like I said, you're going to just have to use the meter method. And whenever I've talked a lot about putting that 33K ohm resistor at your home run and your normal end line at the other. If you don't have a 33K, just use something that's different than whatever your end line is. Because if you put the same resistor at both ends, you're not going to know which direction your trouble's in. But it doesn't actually matter which one you put at your home run, because when it comes time to hook the circuit up, we have to take that resistor back off anyways. It doesn't belong permanently in that circuit. It's just a tool to help us diagnose it. You know, normally I wait till the end to open up for questions, but since I might have, oh man, time's going faster than I thought it was. Does anyone have questions about this before I move into the next spot? All right, I'm going to take that as there's no questions, which that's a good sign. I'm glad we're sticking together so far. This next part I'm going to work on, it's going to get a little more detailed into how the NAC supervision works. I promised last week, whenever I showed you some voltage examples, that I was going to explain why NAC circuits have their supervision voltage in a reverse polarity, but then in alarm, it flips the direction of flow to activate it. And the reason they do that is because they use diodes in the circuit. And it puts out the same or roughly the same amount of voltage to the NAC circuits no matter which way it's flowing. But they put these diodes in there so that the diode can actually allow electricity to flow one direction and stop it if it's coming the other way. The easy way to remember it, if you look at this symbol I have here, that's real big, kind of in the center of the page, it looks like the play pause sign almost. You've got an arrow that points to the right. That's saying it would allow electricity to flow from the left to the right. And then you've got that solid vertical line at the end of that arrow. That acts kind of like a wall. So if your electricity tries to flow in from right to left, it's going to bounce off that wall and have to go somewhere else or just become a dead stop. The picture below it, that's what an actual capacitor looks like if you had the component in your hand. Then over on the right, you see we have a circuit where it shows you've got arrows going around this box. The arrows are showing which way the electricity is flowing. Because it's flowing in the same way that diode works, it's allowing the light to come on. That's what those little yellow lines next to the light mean, if you can see that. If you were to hook the battery up the other way, the arrows would change direction, the electricity is flowing the other way. The light would not come on because the flow would get stopped at that diode. And that's exactly what we're doing with our NAC circuits. So here I drew, it's kind of that same drawing I used earlier where you see the fire alarm panel and the devices daisy chained together ending with an end-line resistor. But now I added current flow and I added the diode symbols. So inside each of our strobes, they put a diode in there because the supervision voltage would actually activate the light bulb in the strobe, whether it's in alarm or not. But adding that diode stops the voltage from coming across the device, forcing it to keep bouncing down the circuit and only come across at the resistor, or it returns back at the panel. And that's what I was talking about earlier with that resistor only allows a specific amount of current to go through, and that's the amount of current that the fire alarm panel is looking for. On our Class B circuits, that's how the supervision works. It doesn't allow any electricity to flow across the device because the device has that diode stopping it. It instead forces it to only come across the end-of-line resistor and return to the panel. And then when you put the panel in alarm, we'll move over to this picture on the right, and you can see I've got the electricity flowing across each device, and it passes down to the next, because electricity is going to go every which direction that it can, always looking for the path of least resistance to get back to its starting point. And so it's going to go across the device, and it's going to go down the circuit looking for more paths back to that starting point. And this is where that water hose analogy picks back up. So if I had a water hose that I fill with water pressure, it's hooked up to a spigot, but I put a cap on the other end of it, that water hose is going to fill up and it's going to be under pressure. And then I walk a foot down the hose and I take a little ice pick or something and I poke a hole in it. I'm going to start having some water pressure coming out there. And I walk another foot or two and I put another hole in it. And I keep doing that. Eventually it's going to get to the point where I have so many holes in it that the water is not spraying out anymore. It's more kind of trickling out. And that's what the idea of a voltage drop is. As you put more and more devices on a circuit, as we get the circuits longer and longer, you have less pressure as the circuit goes on. And so your initial devices that are close to the water source or close to the electrical source, they'll continue to work. But as you get further and further down the line, you're going to have less electricity coming across that device, and you're going to get below the threshold that actually turns that device on. For our system sensor strobes, they work for a range, the low side is 16 volts and the high side is 33 volts. So as long as you've got between 16 and 33 volts at that device, that strobe will come on. Of course, it has to be wired in the right polarity like we're talking about here. But once that electricity drops, you know, you've gotten so many devices down the circuit, once that pressure drops so much that it's below 16 volts, it's not going to turn the device on anymore. So when I'm doing our plans here at the office and I'm putting together our design and I'm drawing out the circuits, I'm taking all the different factors into account, like how much wire is between devices, so that we get how long the run is, how many devices are on the circuit, and what candela settings, which is what load each device takes. All of that comes together to create our voltage drop calculations. I put a page of that into each of our submittals. It's a big giant table. I don't know how many ever take the time to look at that or try to understand it, but it's a table that I put on one of our drawing pages. And if you look down it, you'll actually see that it lists the devices in order of the circuit, and it tells you what the theoretical voltage amount is at each one of those. And we do it that way so that I make sure, one, that we're not going to overload the circuit so you'll have devices that won't work. Also, to make sure I'm leaving enough headroom in there. So if y'all have to make a couple changes here or there in the field, like maybe there's a corridor that's a higher ceiling than I realized, and I have the circuit going across that corridor, but you have another circuit on the other side, and you can kind of trade devices between the two circuits. It gives you enough room to do that without worrying about overloading it. Don't do it too terribly much. Like, don't just completely redraw the circuits, because then all the voltage drop calculations kind of go out the window at that point and we're just guessing. But I do leave enough room in there for you to make some minor changes if there's some unforeseen circumstance. Also, I kind of mentioned it, I want to point it out even more. It's not just the number of devices on the circuit, it's also what the setting of the device is. So like with our strobes, our candela setting, a higher candela would be like having a larger hole in that water hose letting pressure out, and a lower candela would be a smaller hose. The larger hose is going to the larger hole in the hose is going to let more pressure out. The same way a higher candela setting is going to use more current draw of the circuit, which is then going to mean at the end we can put less devices on that circuit. So it's not just how many devices can I put on this circuit, it's how many devices at what candela settings. And also, how long is the circuit? Because just like that water hose, if you make that water hose really, really long, it's going to take a lot more water to pressurize it at the end than it would if it's a shorter circuit. Well, we're dealing with a set amount of electricity coming out of the panel, so we can only go so far with our wire. And then kind of I'm going to try to get through the end of this real quick. I realize we're a little bit over time here. Using our meter to check for reverse polarity on these NAC circuits. This is something I really wanted to show y'all in hand, but my camera messed up. So I'm sorry. Like I said, I'll have to have to make this up on the next video when I get a different camera or something. This is a really simple thing. So if you're already there with your meter and you're checking your circuit and you see, okay, cool, I've got my complete circuit here. I'm standing at my home run. I see all the way to my end of line resistor. Everything's fine. I don't have to do any troubleshooting on this. All you have to do, since we hooked our red to red and black to black, whenever we were checking for that end of line resistor, now all you have to do is remember exactly what number your meter said and flip which wires you hook your meter to. So now you're hooking your red meter lead to your black conductor and your black meter lead to your red conductor, and you're looking at what number that gives you. If it gives you the exact same number, like say you had 4.5 k ohms at first and you're looking for 4.7 k ohm resistor, you know, that's close enough that you can say, oh yeah, I see my resistor. And then when you flip that and you see 4.5 k ohms again, that means you have a device in reverse polarity. I'm not going to get into the big engineering detailed definition of why that works. Just know that if they're the exact same, then you have at least one device on your circuit that's wired backwards. If you get slightly different readings whenever you reverse it like that, that means you're good. You don't have any reverse polarity devices. So you hook it up the red to red and black to black, and you see, oh, I've got 4.4 k ohms. All right. And then you flip it and you see, oh, I've got 4.7 now. That's perfect. That's exactly what you want to see. You want it to be slightly different. Both ways you see that resistor, but when you flip it, you want to see that change because that means all your diodes are facing the same direction. So it's a real quick, real easy thing because you're just moving your meter leads from one to the other. And I want to do a quick reminder about using your meter checking for the ohm. One, don't hook it up to a live panel because you're backfeeding voltage into your panel, and your meter has some safeties built in that'll protect your meter, but the panel doesn't have those safeties built in. So even though your meter is really small and really weak, it can take down a panel. I have seen that happen. The other thing I want to remind you to do, make sure your hands, your skin is in no way touching the bare copper or the end of your meter leads, because that'll mess with your resistance reading and might make you think that you have a device wired backwards when you don't. But again, just remember, if it's the same when you read it both hooked up both ways, then you have a device backward. If they're different, then you're good. And then the very last thing I want to talk about, I'm just going to briefly mention Class A circuits. These are the ones that we rarely see, but they do happen occasionally. We have had a couple jobs in the 10 years or so that Pyrotex has been around that have had Class A circuits. They work almost the exact same as a Class B circuit, except where an end-of-line resistor would be over here at the end. We have this return leg. This is called a redundant path. And what it connects back to the panel. Sometimes you still have to land your end-of-line resistor here. Sometimes you don't. That's more a manufacturer-specific thing. It's still looking for the same amount of current flow going through the circuit. The benefit of this is when you get this broken wire right here in the middle of the circuit, all your devices on both sides still work because your current's able to flow down this redundant path to still light up these devices. And your panel will still tell you that, hey, you have an open circuit, one of your legs is broken. But even though you have that open circuit, all these devices are still going to work. So it's kind of just an emergency redundancy thing. As far as troubleshooting these go, they confuse a lot of people. The way I find that's the best way to do it, come over to this redundant path, disconnect it from the panel, put an end-of-line resistor on it, and then for your diagnostic process, treat it the same as a Class B circuit. And then when you've metered it all out, you've got your open circuit fixed, take your resistor back off, put it back on the panel, turn it back into a Class A, and everything will clear up and be fine. Because we're fairly used to having to troubleshoot and chase down Class B circuits. We're not used to Class A circuits. So just turn it into what you're used to. Make it easy on yourself. And sorry this one ran a little longer, guys. Sorry I couldn't do a hands-on with the meter. I had a few strobes wired up here with the reverse polarity and the correct polarity so that I could show you what that would look like. But if you've got any questions, you want me to go back and revisit anything, let me know. I'm opening it up for questions.
All right, Keith.
Yeah.
When you was talking about the voltage drop, and you say that you draw them out and put it in the notes on our plans. What happens in the case that electricians does all of the pipe work, but he run it super longer than what's expected?
That's another reason I leave that headroom in. So I leave headroom in those circuits in two ways to try to help out with things like that. One, when I start, I don't assume the voltage coming out of the panel is a full 24 or 27 volts. I actually start by assuming it's closer to 20 volts even. So we've already lost a few volts just with the starting of my calculation there. And the other thing I do is I never try to bring the circuit anywhere near that 16 volt minimum. I try to leave you a volt and a half, or 2 volts left, so that if you do have to add some extra wire to go that extra distance, the circuit should still work without overloading. So between
Okay, now is that going to be the same for the speaker strobes?
Yeah, that's the same for the speaker strobes. The main difference there, speaker circuits can actually go a lot longer than NAC circuits go, so much so that it might actually seem speaker circuits are almost unlimited, which isn't actually true, but it can seem that way. Because whenever the speaker circuit activates, it's no longer DC voltage, it's AC voltage. And when you get into all the physics of how all that works, AC voltage actually travels a lot farther than DC voltage. So it's still true of that, but it works even further than our strobe circuits would.
All right.
Okay, are there any other questions? All right, I think next week we're looking at either talking about looking more specifically at SLC, because this really focused on like NAC circuits, or we're going to look at relays and dry contact switching and that kind of stuff, or we'll look at ground faults. I don't know that we've decided on which of those we're going to look at. We're going to do all of them. I just don't necessarily know which order we're going to do them in. So if y'all have any preferences or you're running into specific problems, let me know and we'll try to include stuff like that to help everyone out. But other than that, if there's no more questions, y'all are free to go. Sorry this one took up a little bit more of your time, but hopefully the information helps save some time somewhere else.
Thanks, Keith.
Yeah, we need to go over relays.
Yeah, that was one of the ones I was talking about going over. SLC, relays, and ground faults are 3 coming up. So maybe I'll do relays next week since that's being requested.
That's going to include the elevator too?
Yeah, I'll at least get some into elevator. We might do, I'll look at how much there is to talk about it. If I think relays are going to take up too much time, we'll make a specific one for elevators. If it looks like relays aren't going to take up that much time when I start getting into it, I'll include elevators in that one.
Yeah, sometimes I do have trouble right up in there with the shunt trip and all of that. So that's why I was asking.
Yeah, there's weird ways to wire up shunt trip, and there's weird ways to wire up smoke dampers, and I definitely want to talk about both of those.
All right. Well, let's finish getting my pay.
All right, sounds good.
All right.